Hello, everyone, and welcome. We are back with our MAMNA Fall Virtual Seminar Series. And so I'm Ryan Sokol, co-president of MAMNA, and here is Heidi, our president.
Hi, everyone. So today we have the pleasure of hosting Camilo Velez. He's an assistant professor, a new assistant professor, in the Department of Mechanical and Aerospace Engineering at UC Irvine. His research interests include micro-nano robotics, fabrication of magnetic devices at the microscale, MEMS, and microfluidics. He conducted his postdoctoral research at Carnegie Mellon University in the Microrobotics lab and at the Interdisciplinary Microsystems Group at the University of Florida. Camilo received his Ph.D. and Master's in Electrical and Computer Engineering at UF, a Master's of Engineering at Universidad de los Andes-Colombia, and his bachelor's in electronic engineering at Pontificia Universidad, Javeriana-Colombia. Dr. Velez was awarded an engineering award for creativity at University of Florida, honorable mention for excellence in research in his bachelor's in Colombia, and won 2 Best Poster awards. He currently serves on the Board of Governors of Electron Devices Society at IEEE, and as chair of Young Professionals Committee in the same society. So, Camilo, let's hear what you have for us today.
Thank you, Heidi, and thank you, Ryan, for the invitation. I'm very excited to be here. What I would like to show you today is the work conducted at Carnegie Mellon University in the last couple of years. And this is about actuators for microrobotics and our approach of using some of the microfabrication, additive manufacturing, and shape memory alloys. So first of all, our little micro robots, they start working in the 60s with this idea of trying to put those robots in our body. And the vision has been updated, especially by the movies like Big Hero 6, is trying to have a swarm of robots that can cooperatively work and do something. And right now we have in state of the art is little robots that they can move, most of them magnetically, and the works that they can perform are simple still. We have flying robots that Professor Wood in 2008, and some of the walking robots from Professor Ferry in 2009. This is going to be just examples of this cooperative work. We consider micro robots everything in small scale, like below centimeters. And most of those robots have been tethered, like having just attached to magnetic fields or attached to wires, as you can see in this video. And but they will need to improve a little bit in order to do complex tasks in the future. And right now we have some of these ones that can walk, that can swim, that can fly. And this is a very excited time for microrobotics because there is plenty of opportunities. And one of the most important opportunities is kind of in biology, and the interaction between these micro robots and cells. And here we have some connecting with sperm cells for fertilization. This one is to put it in the stomachs from MIT, just to pick up batteries and patch some infections in the stomach. And we have some interactions with the bacteria, as the one that we saw here. So a little bit the panorama of microrobotics is in the industry of robotics, of course, and that's a growing industry that this last year report around $38 billion in revenue for that year, and it's growing very fast. And you're gonna find microrobots in 2 realms. One is in the medical implants or medical and surgical robots, and the other one was going to be with industrial applications. And just because the type of robots that I'm going to do right now and I'm going to present to you is they require additive manufacturing. I add this market of additive manufacturing that is growing very fast, and it's an enormous opportunity. And in terms of publications, we are growing as a community. We have in total like around 9,000 papers. And of course, we are an infant community compared with with the MEMS community that only last year or 2 years ago, they published 32,000 publications in the MEMS community. And nanotechnology published 64,000 publications. Meanwhile, in total, from the last couple of years, like 30 years, we have 8,000. But this is demonstrated that we are growing at a nice stage. So what I'm going to present today is it was a big challenge created by the Department of Defense, by DARPA, where they're trying to make the little micro robots more functional and try to do different jobs. And they create this program that is called SHRIMP. And it was creating robots with millimeter scale, like 1 centimeter by 1 centimeter by 1 centimeter, that they can integrate electronics, actuators, and the battery itself. So that was the big idea, that they participate in a competition, that they can jump higher, throw something in a shot put competition, long distance, weightlifting, or tug war. It was 14 universities and 3 companies working on this one. And the approach that we took at Carnegie Mellon in Professor Sarah Bergbreiter's lab was let's use the technique that we are right now, the most common available for microrobotics, that is going to be like 3D printing and additive manufacturing. But if you want to do a microrobot with additive manufacturing, not all the 3D printers work. The state of the art of the most used one is going to be the 2-photon polymerization technique. And this is the one that you can find in nanoscribe. As a 3D printer. This 3D printer uses laser, and as I mentioned, the 2-photon polymerization technique is just try to combine a voxel of light, and the polymer is going to be cross-linked, or is going to be polymerized only in that region. And that voxel size is going to have, generally speaking, 250 nanometers in depth, and height of around 1 micron. So that will give us the versatility to make very small machines. But the big question is, from a 3D printed part that is normally a polymer, previously in our group, we start working with multiple materials, but those materials were not active materials. So how can you integrate these 3D printed techniques with active materials, such as your robot can start doing things, and you can start creating mechanisms? So the first approach that we had was, and this was a work mainly conducted by Sukshun and Kim in our group. It's, let's start by 3D printing the material, and let's have the polymerization and the pieces in place. But we design the pieces in such a way that we can coat them or sputter them with a normal microfabrication technique, sputtering, with aluminum or a conductive material. And what we're going to do in the design or engineering the shapes is we're going to leave some gaps underneath the structures, such as we break the electrical conductance of the aluminum. So we are going to have areas that are conductive and non-conductive. And with this approach, we manage to create some thermal actuators. That's the first step into an actuator. You're going to pass current through one of the beams. The beam is going to heat up more than the other one because of the aspect ratio of the shape, and this one is going to deform in a different rate than the big one. And by using this approach, we prove that we can make actuators with only 2 steps: only 3D printing, and afterwards sputtering of metal, of a metal. We test these devices, and we can manage to actuate this up to 8,000 cycles. So those are reliable actuators that could be used for prototyping. We move a step forward and we test electrostatic actuators. So in this case, you just apply electrical field between these two ports, and the there's going to be a capacitance on those fingers. It's a common microelectromechanic machine and technique. And you're going to generate electrostatic force that are going to attract this comp drive that we call. And we can generate displacements of around 12 micrometers, of course, with high voltages than the other one. And we can, the big advantage of a 3D printer is that you can do very crazy shapes. And for example, these wings were entirely 3D printed, and then you just sputtered the material in a single process, and you manage to have these flaps or these wings flapping in the air and producing these type of shapes. There is a lot of mechanisms that can be designed now if you have a 3D printer. But again, the big question from DARPA is how can you make better mechanisms or better in terms of work? So we want to increase the work density of our actuators. And to do so, we need a material that can deliver high work. So in the materials that are right now currently available, you have the electrostrictive polymer, but the gain is not so much, and the stress that you can generate is not high enough. You can have like piezoelectric, magnetostrictor, but the material that right now it has a better form factor for the work density. It's going to be the shape memory alloy. Our group also conducts some research on germanium telluride, but the part of the project that I'm going to present right now is just the shape memory alloy. The other one is just a phase transformation material. So how does this material work? So first of all, the shape memory alloy, it's a metallic alloy that has the characteristic that you can see on your right. When you increase the temperature on the material, there is a point where the material change or perceive a phase transformation. So from Martensite is going to start an austenite phase. And during this phase transformation, there is a huge stress that produced by this material. Whenever you cool down the material, the stress is going to be relieved and it's going to return, but it's not going to return in the same way. It's going to generate this hysteresis curve. And this is exactly what we are trying to extract from this material, this hysteresis curve, because it means that we can generate more stress in this sudden transition from the martensite to the austenite. And I'm going to mark this transition from the AS and AF, like the starting of the austenite and finish of the austenite, and MS and MF, like starting of the martensite and finish of the martensite. The way to heat up this one is going to be by Joule heating. It means that we are going to apply a current through the shape memory alloy, and by applying the current, we're going to heat up the material. And if we have a passive layer on top of that, we are going to see that the material is going to deform. And if originally, because of the stress of the material, is curling up, and you apply the current, you're going to heat up the material, and this is going to curl down. And the reason why it's curling down is because the mismatch of stress between the shape memory alloy and the passive layer on top. So guess what? The passive layer that we're going to use is going to be a 3D printed material. So for this experiment, what we're doing is a common microfabrication. So we have a silicon layer. We co-sputter nickel titanium and a 50-50 rate, more or less 50-50 rate. And then you pattern the nickel titanium, and then using ion milling. And after you pattern the material, you 3D printed the polymer. The polymer that we select was IPS for nanoscribe. That came from the vendor because of the stress that we want to generate on this ones. And after you 3D print, and it's going to look like this for a single beam actuator, you release or etch some of the silicon underneath the actuator. So you're gonna have like a floating cantilever that is going up, is bending up. And when you apply current, as you can see in this picture, when you apply current, the cantilever, it's gonna bend down. And that's how you generate the force. So we generate some models for this one. We use analytical models, and we use also console simulations for this one. At the beginning, we just trying one single cantilever without passing current, and we were heating externally. And we corroborate the implication of having a different thickness on the passive layer. It means on the 3D printed part, in the actuation of the material, in the initial deflection, and then in the stiffness of the generated material. And it's very interesting because we have a very good agreement between our predictions and the model. And what you can understand quickly here is there is going to be an optimal thickness for this 3D printed part, such as you're going to have the maximum initial deflection. And this was only possible. And look, you can by 3D printed, you can have only one wafer with the same nickel titanium pattern, but then you 3D print on top of that multiple configurations of different thicknesses of the passive layer. And this was amazing because it speeds up the process incredibly. You have a very robust actuator at the end, but this is 3D printed actuator. So for prototyping, it's amazing. It's a very robust technique that you can leverage for designing your actuator in the future. We also characterize the change in temperature and the deflection. This was using a thermal camera, the infrascope. And when we pass current, how this is heating up, and we compare with our simulation. This was the console simulation that we had here. Again, some good agreement, but we were improving the technique, so we can always do a better job in this one. But at the end, we managed to 3D print very complex patterns, like this one's here. This is the CMU logo, and well, in non-COVID situations, I will have the pipe, the bagpipes sound on the back side of this, but otherwise it's going to be crazy in the presentation. But you can have actuators with very incredible shapes. But more than having a 3D printed nice part on top of it, what we are going to do is using this for energy efficiency. So we demonstrated, and this is a work from Manoush Babey and our team, that by patterning the polymer, we can increase the efficiency, because we are going to reduce the bulk material that we need to heat up and cool down, and we can increase the stiffness of the passive layer. So we actually can engineer this, and we reach some enhancement on the energy efficient up to 800%. And that was wonderful, because now you're taking full advantage of the 3D printed in your normal microfabricated patterns. So trying to move forward into this project, we try to integrate these actuators with more complex mechanisms. And what we are calling here hierarchical integration of thin film actuators, it's gonna be just simply, it's gonna be simply integrate not only one finger, but multiple fingers with the 3D printer. In this case, we are presenting here 8 fingers just to increase the force that we are creating with these patterns. And we are making an array of 6 of these actuators. So as you can see here in this hexagon, this is going to be the central piece of the cornerstone of a more complicated actuator that is going to be in the center of this one. So you can see how we're trying to microfabricate the actuator, but we are trying to use it to produce forces in the millimeter scale, and to produce bigger actuators, or more stronger actuators that can work in the real world. So one of the most important tests that we perform on these actuators, because at that scale, it was very difficult to find the hysteresis curve. You can find the hysteresis curve on the thin film when you deposit on the wafer, and you can measure the stress on the wafer. But once you release the actuators, you don't know if you are actually going through a phase change, or if you are taking advantage of the shape memory alloy at all. So one of the tests that we observed based on the literature was the resistance measurement. And this was very accurate and very insight, because we generate this type of plots where you just change the current, and by changing the current, you are changing the temperature. And if you change the current back and you measure the resistance, you are also getting the hysteresis during the Martensite transformation. So if you notice this one, it doesn't look like the other shape for the stress, but it's a good indication of the transition of the material. And it's an easily available testing for MEMS applications, because you don't need to measure forces, you don't need to measure stiffness, you can directly measure resistance on the device. And it's very simple, and it gives us these curves that helps you understand the material. I think I have 2 questions on the Q&A. Do you want me to answer right now, or we'll let them at the end, Ryan?
I'll ask you at the end. We have a whole bunch,
Okay,
and so I'll ask you at the very end. So don't worry about
okay. Perfect. So I'm going to continue. And this was for measuring this resistance measurement for 6 devices in one of the ring oscillators. We also perform the temperature analysis, and we compare in the temperature analysis, we change the currents. Right now, we fix the thickness of the polymer that we want. We find kind of the best one for us for having higher force. And we change the current to deflect them. We measure the temperature, and we also, in a separate measurement, we measure the deflection. So we can correlate the deflection and the temperature. And finally, you can measure the force on these devices. We use a femtotools. It's a direct force measurement, a capacitive measurement. It's a capacitive sensor that moves a tip, and physically you're measuring the force on the actuator. And you can find that the displacement, you are getting displacements up to 17 microns, and forces up to, in general, like 1.2 1,200 micronewtons. So those are millimeter scale forces that you can actually use in a micro robot to win a competition at some point, but made out of microfabricated and 3D printed actuators. And some of the questions that we had on reviewers at some point, it was, wait, but it's 3D printed, it's just a prototype. Yes, but it's a prototype that can work up to 5,000 cycles on this one. We tested these ones for 5,000 cycles and with a variation of less than 12%. So for prototyping purposes and university purposes, it's very robust technique. And again, if you compare this with the environment that you had in the past with the transistors, all the transistor was microfabricated with a big lithography mask, but the gate, the most important part of the transistor, usually was using a technique like e-beam writing, that it was a sequential technique. So you can think about this technique for a batch fabrication of a 3D printed, of microfabricated part, and the most important, that is the beam itself, you can 3D print it in a serial pattern. So it has a huge potential. So I'm going to show just the final video of our our actuator integrated with a microcontroller and a battery. This was completely unconnected to external power supply. That it was moving all the actuators on the hexagon, and you can control the hexagon actuation. You can actuate it by pairs, you can actuate it individually, you can actuate them all at the same time. So this is a proof of concept that we can create a more powerful mechanism based on our actuators. And here we're just presenting a 3D printed part. This is a mesoscale 3D printed part. This was made on a SIGA. So this is a millimeter size part that you can integrate in this actuator. And right now we were demonstrating like a positioning mechanism that you can control the position, but you also can use this as a torrent to just integrate it with a ratcheting mechanism and actuate this one. So in conclusion, we demonstrate the ability to integrate 3D printed with microfabrication to create very powerful actuators that generate a lot of work that can be used in the millimeter scale, that this is what we want. This is stable up to 5,000 cycles, and it's very cost effective for prototyping. So of course I want to thank, and I'm gonna have 2 more slides after this one. I want to thank the team, especially Sarah Bergbreiter and his team. This was conducted with Gianluca Piazza and Ajim Bain, sorry, I forget to update his name, Manoj Babay, Dinesh Patel, Sukshum Kim, Mohammed Ajaz, and James Best. And all the nickel titanium was in a collaboration and was provided by the Army Research Lab. So we have been working with them, with Corey, Gabriel, and Wayne. And thanks, of course, for DARPA. And one vision to the future. So as Ryan mentioned and Haley mentioned, I recently joined University of California, Irvine, and I'm creating my laboratory that is called Magnetic Microsystems and Microrobotics Lab. And our vision is to create a swarm of functional robots the size of a cell that are trying to work together to solve complex problems by themselves. And the way that we're doing that is giving them more autonomy, so increasing the autonomy. So I'm going to be working, and this is just a sneak peek into the future. I'm going to be working on advanced manufacturing of magnetic materials, combining the 3D printing with magnetic materials. We need to combine some biohybrid and biopower micro robots that can work with cells, that can work inside the body. And of course, at some point, create a swarm of micro robots that work on tether just to do a job, like the ants, the bacteria, and the cells does in your body or in the nature. That we need to create a swarm of robots to work cooperatively. And everything here, again, is for we need to work towards gaining micro robot autonomy and try to solve medical and manufacturing industrial applications. So with this one, thank you very much, and I'm open for any questions from the audience.
Yeah. All right, so we have a ton of questions. So we're gonna try to rock through as many of these as possible. So one of our first questions, actually, you already addressed in your slides. And so Michael Barron had asked, how many cycles can you achieve until failure for the NiTi? I think you mentioned 5,000 cycles, right?
We test 5,000, but we didn't find failure. In another test, we did 8,000, and again, haven't found failures yet. So we haven't done a systematical approach to find out what is the limit of these ones. Because it's highly dependent with the current that you are applying. Of course, if you start increasing the current, or if you start pulsing to generate higher efficiency, then you're gonna start damaging your device at some point. So if you keep the current in the sweet spot of you are transitioning the phase material, you are transitioning phases in the material, but not damaging the polymer, you're not reaching to the deformation temperature of the polymer, you can have many cycles. We haven't proved how many at the end.
And then Aaron Mendelson asked for context, is a variation of plus or minus 12% significant?
That's a good question. So for the competition that we were trying to win and with DARPA, it was perfectly fine. We are not targeted a number at this point, and we were thinking for our robots on roughly 5,000 actuations. So that was the goal of our project. That's why we didn't extend beyond that one. But it could be improved, and in fact, we improve in the future just by tweaking a little bit the printing techniques. So to be more reliable on the fabrication. At the beginning, we have some parts that were not very well printed, and we were comparing with the ones that were well printed. So if you are very robust with the 3D printed, that number we're gonna decrease substantially. And the other factor is, that's a research question that we're trying to address at this point, and hopefully in the future, is the reliability of the nickel titanium layer through the entire wafer. We observed that there are sections of the wafer that have, of course, like any microfabrication process, and this is the same problem in semiconductors. It's how to make the most, how can I say, like the most reliable material through an entire wafer. And that's something that we haven't been able to study, and we can study now that we have the measurement of the resistance in place. That's something that we are very interested in pursuing soon.
Great. So we have a question from one of our MAMNA members. Mac has asked how the NiTi cantilever is released from the silicon substrate, and did the NiTi require any kind of protection layer?
Sorry, it got caught. Is how to release the cantilever?
Yeah, how are the NiTi cantilevers released from the silicon?
Perfect.
And did they require any kind of protection layer?
Thank you very much. That's a great question. Perhaps I failed to mention this one. The etching was made using xenon difluoride. So that's an isotropic etching. The only protection that we had at this moment is the polymer itself. So the 3D printed polymer serves as protection layer for the rest of the etching. And the other parts are the nickel titanium. The nickel titanium are not going to get etched by the xenon difluoride. So that's the best technique that right now we had, is because it's gonna create that undercut, and you can notice here it's gonna create the undercut everywhere else. An important note is that you need to engineer some trenches in the actuator, such as the xenon difluoride can go uniformly through the entire actuator, and you don't have something that is released on half of the actuator and the other half is just attached. But if you cover that, xenon difluoride is a perfect technique.
So one of the questions that was asked from Aaron Farrell was actually one that I was going to ask as well. So is the goal to use this additive manufacturing strategy and sputtering purely just to make the prototypes, right? So you had kind of like a number of designs, where like 3 micron thickness, 7 micron. Are you using it purely just for the prototyping stage that would eventually be mass produced using another type of manufacturing, such as conventional manufacturing, because most of the designs look relatively planar?
That's a good question. At the beginning, we thought so, but as we show here, the ability, when Manush's team did the simulations and the analysis of this one, and she discovered that by patterning the photoresist in a certain way, you can improve the efficiency. Now it was clear for us that these type of patterns are very challenging to fabricate in normal lithography, in conventional lithography process. So if you try to get that triangle shape or this I-beam that we're presenting in the picture, that's challenging for photoresist alone. So we understand that if we can take advantage of the 3D printed part, we can leave the 3D printed part in the actuator itself, and it's integral part of the actuator in the future. Of course, for mass production, as I mentioned to you, perhaps you don't need to 3D print all the entire actuator. You only need to print like the beams here, and that will generate a high throughput in the overall process. But the first goal was prototyping, and then we discovered that we can leave the material there, and it's very robust for actuation in the future.
Great. So we had a couple questions on the temperature properties. So Corey Nick asked, will this be easily extensible towards high temperature applications or cryogenic temperatures? And similarly, Daniel K asked about how long does it take to heat or cool, and does it need or have you considered a cooling apparatus?
Very good questions. To Corey, the first question is, in our project, we were trying to study GET, German telluride, because that material can sustain higher temperatures. So with that, in that part of the project, we went up to 700 Kelvin for the applications. So if you were going to use very high temperatures, I recommend just to think in a different material, just because we find out that, and not taking a different material from the nickel titanium itself, but also from the polymer. The polymer cannot sustain more than 225. I think that was the temperature that we start degrading the polymer in the future. So if you are planning to use high temperatures, we need to engineer a little bit different the material itself. For prototyping is good, but the polymer needs to withstand higher temperature, and the nickel titanium also needs to have a phase transformation in a higher temperature as well. Now, for lower temperatures, we can also, I mean, the actuator can work at lower temperatures, but the current is going to heat up. I mean, this is a thermal actuator, so we need to heat up the polymer below 100 Celsius, heat up the nickel titanium, the shape memory alloy, above 100 Celsius to get a phase transformation. So the current needs to pass and heat up the material, otherwise you're not going to experience any actuation. If you change the composition, and this is for 50-50, if you change the composition of the polymer, of the nickel titanium, you can shift the hysteresis curve at lower temperatures. And I'm not so sure, we haven't demonstrated how low can we go in that direction, but it can be tunable as a certain amount. I won't promise that at freezing temperatures it's going to work. I'm not so sure. I will need to work on that one. And the second part of the question, can you repeat that one, please, Ryan?
So the second part of the question was, what is the response rate on the actuator? So how long does it take to heat and cool? And does it need, or have you considered a cooling apparatus?
Very good question. And the reason the cooling rate is in milliseconds. So usually it's heated up below 10 milliseconds, around between 1 and 7. It depends on how big is the device. And the cooling rate is also in milliseconds. We have not considered using a reducing temperature apparatus, but because we took this approach, we try to engineer the beam such as it cools faster, because it's less material to cool down. And so that's why we took this approach instead of trying to put a different material and try to make a little bit more complicated the actuation. It can be done, but this has been tested so far in room temperature environment.
So I think the last question I'm going to ask in terms of timing today. So this is from Nathan Brown. Are there any other materials that you're considering other than NiTi that would provide better material properties for the kind of applications that you're considering?
Yes, as I mentioned, one of the materials that we are working with is GET, German telluride. And please stay tuned for the most updated results. We don't have it published yet, so I'm not gonna present it here. And the other collaborators, especially Gianluca Piazza, part of the group, conduct that part of the experiment. And that's a material that is going to give us, it could give us a higher work density, but the temperature that you require to actuate and change phases, it's also higher. So the challenges are completely different, and the materials that you will require to work with are completely different. But yes, it could be done. Great.
All right. Well, thank you so much for presenting, Professor Velez. Yeah, officially professor. I guess that sounds great.
Thank you very much.
Anyways, thank you so much. And thank you everyone for tuning in. So next week, we're going to have actually Professor Daniel Cohen from Princeton University, who's going to be presenting on collective cell migration and cell stimuli. But with that, I want to thank Professor Velez one more time for coming and sharing all this content on 3D printed / microfabrication based microrobotics. And I know that there were a number of questions that we didn't get to. Potentially Professor Velez is able to, once the comments are back online. It takes a little bit of time to process, potentially to be able to answer some of those offline after this. But for now, I want to thank everyone, and we hope to see you potentially next week. Bye, everyone.
Thank you, Ryan. Thank you, Heidi. Have a good day.
Okay, I think we're good.